Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Welcome to the Deep Dive. Today, we're really digging into some of the most influential systems around us. Think about recommendation engines, search algorithms, those automated assistants, even sophisticated sensors, systems that seem to, think for us. I mean, just look around. These technologies, they're constantly perceiving, predicting, making decisions that genuinely impact your daily life. And when we talk about these systems, often lumped under that, catchy AI banner, we hear terms like machine intelligence or cognition. But our mission today, looking at the fantastic source material you shared, is to get past that feeling of magic. We want to understand the actual logic, the architecture, the sort of mathematical skeleton underneath it all, and the limitations too. How does raw data really become a concrete choice?
Yeah, and it's absolutely critical we start right there. We have to make that core distinction up front. Otherwise, none of this will make sense. Machine learning systems, they don't think, not in any cognitive sense. There's no consciousness, no intent, no real contemplation going on. What they do execute is let's call it a sophisticated choreography. It's all mathematical operations, finding statistical patterns, logical transformations, the decisions. They're predictions that come from optimizing enormous equations. It's fundamentally statistical optimization, not human-like thought.
Okay, right. Optimization, not thought. So let's unpack the journey from the very start. If it all hinges on data, what are these systems actually, consuming? What does raw data look like to an algorithm?
Well, the universal truth here is that no matter its form in the real world, a photo, a stock price, a sound wave, whatever, it all has to become numbers first. Specifically, they get turned into these high-dimensional numerical things: vectors, matrices, tensors, stuff ready for linear algebra. Our sources break this down into about four main types. The easiest is structured numerical data. That's the neat stuff, right? Sensor readings, timestamps, customer ages, financial transactions. Right. It's already in nice rows and columns, pretty much ready to go. Manageable.
That sounds like the ideal scenario, the clean data. But modern AI, it really thrives on the messy stuff, doesn't it?
It really does.
Okay.
So next up is unstructured data. This needs a lot of complex pre-processing before it's useful numbers. Think about a photograph. To the machine, it's just an array of pixel values, red, green, blue intensities, maybe 0 to 255.
Okay.
Text, just a string of characters. It has to be converted, maybe into numbers representing words in a dictionary, or more recently, these dense embedding vectors that try to capture meaning.
Meaning in numbers.
Sort of. The idea is that words with similar meanings, like cat and kitten, end up being numerically close in this vector space.
Rough.
Audio, that's just a sequence of sound wave amplitudes over time.
Right.
So yeah, transformation's pretty involved.
Right.
Then there's semi-structured data, kind of a bridge between the two. Think web server logs, JSON files, XML. They have some organization, some hierarchy, but not that rigid row and column database structure.
Okay, so structured, unstructured, semi-structured, and the last category, the labels.
Exactly. Categorical data. These are the discrete labels that often define what we're trying to predict. Movie genres, spam, or not spam, colors like red, green, blue.
And how do those become matte? You can't just say red 1, green 2, right?
No, you definitely can't do that. The algorithm might mistakenly think blue is somehow more than red, or that there's an order. That's usually meaningless for categories, so we use things like one-hot encoding. It turns each category into its own sort of binary switch. Red might become 1, 0, 0, green 0, 1, 0, blue 0, 0, 1. Each one is distinct, no accidental ordering.
Got it. So the very first step in this whole pipeline is this act of radical abstraction. Taking real things, faces, words, prices, and turning them into these giant numerical coordinates in some high-dimensional space.
Absolutely. And the very last step, of course, is the reverse. The model spits out a number, maybe probably like 0.9, or a value like $500. And that has to be translated back into something actionable in the real world. Showing a specific movie, approving that loan, telling a car, hit the brakes. That transformation back really bookends the whole process.
Okay, let's walk through the architecture then, the main pipeline. Because as you said, data never arrives clean. It comes from sensors, user clicks, databases. It's always messy, incomplete, inconsistent. So what's the absolutely mandatory first stop?
Data prep. Data preparation. Honestly, you talk to practitioners, they'll often say this is like 70, maybe 80% of the entire effort in a machine learning project.
Yeah, really.
Yeah, data quality is just paramount. You can have the most sophisticated algorithm in the world, but feed it garbage data, it'll just find very sophisticated patterns in that garbage. Garbage in, garbage out, as they say. So preparation involves a few key things. You've got to handle missing values. That's called imputation. You often can't just delete rows with missing bits. Sometimes the fact that it's missing is informative itself.
Oh.
So you might fill the gaps, maybe using the median value for that feature, or use more complex interpolation, or sometimes even build a little side model just to predict what the missing value likely was.
And what about outliers, those weird data points way outside the norm?
Outlier detection is critical and tricky. Is that point a genuine, rare, but really important event, like a huge financial transaction that signals fraud? Or is it just a sensor glitch, a measurement error you should fix?
That sounds like a tough judgment call.
It is, because if you treat a real anomaly as just an error, you're throwing away potentially vital information.
We also need to touch on scaling and normalization. Seems technical, but you mentioned it's crucial.
What? Absolutely critical. Scaling and normalization basically ensure fairness between features.
Right.
Imagine you have two features for a customer. Their annual income may be hundreds of thousands of dollars, and their click-through rate, a number between 0 and 1.
Okay.
If you just feed those raw numbers into certain algorithms, especially distance-based ones, the huge income numbers will completely swamp the tiny click rate numbers, just because they're bigger magnitudes. The algorithm might overweight income simply because the numbers are larger, not because it's actually more predictive.
Ah, I see. So you need to bring everything onto a level playing field.
Exactly. Normalization typically rescales everything to a similar small range, like 0 to 1, or standardizes features, so they have a mean of 0 and a standard deviation of 1. This lets the predictive power of the feature determine its importance, not just its raw size.
Okay, so the data's clean, it's balanced. Now we hit what people often call the art of machine learning, feature engineering. How do we go from just measurements to truly informative representations?
Yeah, art is a good word for it. Feature engineering is really about injecting domain knowledge, creativity, into the numbers to help the algorithm out. You're transforming raw measurements into features that hopefully capture the underlying patterns better. Take that timestamp we mentioned. The raw date and time might not be that useful on its own, but if you engineer new features from it, like hour of the day of the week, maybe a flag for, is it a holiday? Suddenly you've given the model crucial context.
So you're kind of pre-digesting the data for the algorithm, creating concepts it can latch onto more easily.
That's a great way to put it. Instead of forcing the algorithm to figure out that weekends behave differently just from raw timestamps, you explicitly tell it this is a weekend. For text, raw characters are useless. Feature engineering turns them into maybe word counts, or TF-IDF scores, which weight words by importance, or these days, those embedding vectors we talked about, where similar words cluster together numerically. Even with images, you might do some initial processing, like edge detection or contrast adjustments to highlight important visual structures before the main algorithm even sees it.
Okay, now we're really getting to the core. Pattern recognition. This is where the machine starts figuring things out on its own, discovering patterns implicitly, not following pre-written rules. What are the main ways, the main paradigms for this learning?
Right, this is the heart of ML. We usually talk about 3 major learning paradigms, based mostly on what kind of data you have and what you're trying to achieve. First, and probably the most common, is supervised learning. This is what you use when you have labeled examples. You have the input, and you know the correct output you want, like learning with flashcards.
Okay, input and correct answer.
Exactly. The algorithm's job is to learn a mapping function. How do I get from this input, say the features of an email, to the right output, the label spam? And the way it learns is by defining an objective function or a loss function. It's basically a mathematical way to measure how wrong the model's predictions are. The entire goal of supervised learning is then to tweak the model's internal knobs, its parameters over and over again, using calculus to minimize that error, to get the loss as low as possible. This is the basis for most prediction and classification tasks.
So supervised learning is all about learning a known relationship. Input maps to known output.
Correct. Now contrast that with unsupervised learning. Here you just have the raw data. No labels, no right answers provided. The machine's task is pure discovery. Find interesting structures. Classic examples are things like clustering. Think k-means. You give it customer data, and it groups customers into distinct segments based on similarity without you telling it beforehand what makes a good segment. Or dimensionality reduction. Techniques like PCA. The system finds ways to compress the data into fewer dimensions while keeping the most important information. It helps us visualize complex data or speed things up later.
So it's finding hidden structure that we might not even know is there?
Exactly. It can reveal patterns humans might miss because we're just not good at visualizing things in, say, 500 dimensions.
Okay, prediction versus discovery. And the third one, reinforcement learning. That sounds different again.
Reinforcement learning, RL, is quite different. It tackles sequential decision-making in an environment. There's no big data set of right answers. Instead, an agent learns through trial and error. It takes an action, observes the result, and receives a reward if it was good, or a penalty if it was bad. It's like training a dog with treats.
Oh.
This creates a feedback loop. The agent's goal is to figure out a strategy, a policy, that maximizes its total cumulative reward over time. This is the powerhouse behind AIs to play games like Go or chess, and it's crucial for robotics, autonomous systems, anything that needs to learn optimal behavior in a dynamic world.
Right. So once you've picked the paradigm, supervised, unsupervised, RL, the machine needs a specific tool, an algorithm, a model architecture to actually do the pattern finding. I understand there are different sort of philosophical approaches here.
Yeah, different ways to carve up that feature space, essentially. We can broadly categorize them, maybe into 4 main families, each with pros and cons regarding performance, how easy they are to understand, how much data they need. We can start with linear models. These are kind of the foundation. Think linear regression for predicting a value, or logistic regression for classifying between 2 groups. They try to solve problems by drawing a straight line or a flat plane or a hyperplane in higher dimensions to separate the data or find a trend.
Simple, clean.
Very simple, very clean. They're super efficient, don't need tons of data, and they're incredibly interpretable. You can look directly at the weight assigned to each feature and see exactly how much it influenced the final decision.
But reality's messy, right?
Ah,
Things are rarely separable by just a straight line. What then?
exactly. That's where tree-based models, especially ensemble methods, really shine. A single decision tree works by asking a series of simple yes-no questions about the features, like a game of 20 questions. This splits the data space into rectangular regions. But a single tree can be unstable, prone to overfitting. The real power comes when you combine many trees. Random forests do this by building hundreds of trees on slightly different subsets of the data and features, then averaging their predictions or taking a majority vote. This smooths things out beautifully. Even more powerful often are gradient boosting machines, GBMs. These build trees sequentially. Each new tree specifically tries to fix the mistakes the previous trees made. It focuses on the errors, the residuals. The step-by-step correction often leads to state-of-the-art performance, especially on structured tabular data.
Interesting. Okay, trees handle nonlinearity by combining simple questions. What about the big one everyone talks about? Neural networks.
Right, neural networks and deep learning. These are the engines behind the current AI boom. They're essentially stacks of layers, and each layer performs mathematical operations, often nonlinear ones. Because they're deep, meaning they have many layers, they can learn hierarchical representations. The early layers might learn very basic features, like edges or corners in an image. Middle layers combine those into textures or simple shapes, and the deeper layers combine those into abstract concepts, like recognizing a whole face or a specific object.
So they learn complexity layer by layer.
Precisely. And we see specializations too. Convolutional neural networks, CNNs, are brilliant for images because they use filters that slide across the image, looking for patterns. Recurrent networks, RNNs, and especially transformers, are dominant in processing sequences like text or time series data because they can handle dependencies across the sequence.
Transformers are everywhere now, it seems.
They really are. Their attention mechanism proved incredibly powerful for language and is now being applied much more broadly.
Okay, one more architecture family. Support vector machines, SVMs. These sound mathematically elegant, but maybe less common now.
They are elegant. SVMs have a really cool objective. Instead of just finding any line to separate the classes, they explicitly try to find the line that creates the widest possible street or margin between the closest points of the different classes.
Yeah.
They want the maximum possible separation.
Maximum margin. Okay.
And their real cleverness often comes from the kernel trick. Imagine your data points are all mixed up in 2D, like a crumpled piece of paper, impossible to separate with a straight line.
Yeah.
SVMs can use a kernel function to mathematically project that data into a much higher dimensional space, maybe even infinitely dimensional. In that higher space, magically the crumpled data might just pop open and become linearly separable.
Wow.
So the SVM draws a simple hyperplane, a flat separator, in that high dimensional space. When you project that boundary back down to the original 2D space, it becomes a complex, curvy, nonlinear boundary. It solves a hard nonlinear problem by turning it into an easy linear one in a different space.
Okay. That is clever. Okay, this is a perfect lead into the next bit. The actual mathematics and geometry going on here. We need to make this idea of a high-dimensional feature space more concrete.
Right. So as we've been saying, every single data point, every person, every video, every transaction is just a point plotted in this mathematical space. If you have, say, 500 features describing it, that point exists in 500 dimensions. The algorithm's job, geometrically speaking, is usually one of two things. Either drawing boundaries to separate clouds of points belonging to different classes, that's classification, or finding the centers of those clouds, that's clustering. It's all geometry, just in dimensions we can't easily picture.
And the huge shift, the thing that really powered modern AI, was moving from humans painstakingly defining those features, like telling the machine, look for whiskers or look for triangular ears, to detect a cat, to the machines learning the useful features themselves. That's representation learning.
Right. Exactly. Deep learning, in particular, automates that feature engineering process we discussed earlier. The network starts with raw pixels, or raw characters, and layer by layer it learns increasingly abstract and useful representations on its own. The early layers are doing basic feature extraction. The deeper layers are composing those into complex concepts. It's learning the right way to look at the data to make the final task easier. This ability to learn representations is what unlocked progress on really hard problems like complex image recognition or natural language understanding. It automates what scientists used to do by hand, finding the right abstractions.
But this whole structure, all these layers learning representations, it's all useless unless something drives the learning process itself. That engine is optimization. How on earth does a model with maybe millions or even billions of parameters adjust itself efficiently to get better?
Yeah, learning is optimization, and it's all driven by calculus, essentially. You start with that loss function we mentioned, the measure of how wrong the model is. Think of the loss function as defining a landscape, maybe a hilly, bumpy terrain. High points on the landscape mean high error. Low valleys mean low error. The goal is to find the lowest possible point in that landscape, the minimum loss. The main tool for navigating this landscape is gradient descent. Imagine you're standing on that foggy, hilly surface, blindfolded. You want to get downhill to the valley floor.
Right.
Since you can't see the whole map, you feel the slope right under your feet. That's the gradient. It tells you the direction of steepest descent. So you take a small step in the exact opposite direction, the direction of steepest descent. You repeat this. Feel the slope, take a step downhill, over and over, until you can't step downhill anymore. You've hopefully found a valley, a local minimum.
That makes sense as an analogy, but calculating that slope, the gradient, for potentially billions of parameters, that sounds computationally nightmarish.
It would be, except for a truly clever algorithm called backpropagation. This is really the engine that made training deep neural networks feasible. Backpropagation is essentially a very efficient way to apply the chain rule from calculus. When the model makes a prediction and you calculate the error at the output, backprop sends that error signal backwards through the network's layers. As it goes back, it efficiently calculates exactly how much each weight and bias in every layer contributed to that final error. And therefore, it tells you precisely how to adjust each of those parameters, which direction, and how much to reduce the error next time. It distributes the blame, so to speak.
And this adjustment process, it's not usually one giant step based on all the data, is it? You mentioned things like stochastic gradient descent.
Right. Calculating the true gradient using the entire massive data set at once, that's batch gradient descent, is often way too slow. So stochastic gradient descent, SGD, takes a shortcut. It estimates the gradient using just a small, random mini-batch of data points at each step.
So it's an approximation.
It is. It makes the path downhill much noisier, more zigzaggy, but it's vastly faster overall, and often helps escape shallow local minima. Then you have more advanced adaptive methods like Atom Optimizer, which are very popular now. They cleverly adjust the learning rate for each parameter individually during training, letting some parameters learn faster and others more cautiously.
And the choice of that loss function itself really matters, doesn't it? It shapes what the model actually learns to prioritize.
Absolutely. If you use mean squared error, you're telling the model, try to get your predicted value as close as possible to the true value. If you use cross-entropy loss, common for classification, you're telling it, be confident about the right answer and be really penalized if you're confidently wrong. You can even design custom loss functions. If you care more about, say, fairness between groups than overall accuracy, you can try to encode that preference directly into the math of the loss function. The loss function is the goal you're telling the machine to optimize.
Okay, so we're training the model, driving down that loss. But here's the big paradox, right? the generalization challenge. If the model gets too good at minimizing error on the specific data it trained on, it might just memorize that data, including all its noise and quirks. It fails to learn the underlying general pattern. That's overfitting. How do we stop it from just memorizing?
That's the constant battle, and the main weapon against overfitting is regularization. Regularization techniques are essentially mathematical penalties or constraints added to the learning process that encourage the model to be simpler. And the intuition is that simpler models tend to generalize better to new, unseen data.
Keep it simple. How does that work in practice?
The most common types are L1 and L2 regularization. They both add a penalty term to the loss function based on the size of the model's parameters, its weights. L2 regularization, also called weight decay, penalizes large weights. It encourages all the weights in the model to be small, close to zero. This tends to make the model's decision boundary smoother, less jagged, less likely to fit the noise. L1 regularization is interesting because it penalizes the absolute value of the weights. This has the effect of pushing the weights of unimportant features all the way down to exactly zero. So L1 acts like an automatic feature selection tool. It creates sparse models by zeroing out features it deems unnecessary.
And for the really huge neural networks, there are other tricks too, right? Like dropout.
Yes, dropout is a very clever and widely used technique specifically for deep networks. During training, for each batch of data, you randomly drop out, temporarily disable a certain percentage of the neurons in their connections.
Just switch them off.
Temporarily, yes. It forces the network to learn redundant representations. It can't rely too heavily on any single neuron or pathway because it might disappear in the next batch. This makes the network much more robust and less likely to just memorize specific paths through the network for specific training examples. Another key technique is early stopping. You don't just monitor the error on the training data. You also keep track of the error on a separate chunk of data the model hasn't trained on, called the validation set.
Okay.
You keep training as long as both the training error and the validation error are decreasing. But the moment the training error keeps going down, but the validation error starts to creep up, that's the sign. The model is starting to overfit, memorizing the training data at the expense of generalizing. So you stop training right there and keep the model from that point where it performed best on the unseen data.
That makes a lot of sense. Okay, let's shift gears slightly. For really important decisions, medical diagnosis, self-driving cars, just getting a prediction isn't enough. You mentioned sophisticated systems can also say how confident they are. How is that uncertainty actually calculated and used?
Right, this is crucial for trust and safety. It involves adopting a more probabilistic perspective. Instead of the model just outputting its single best guess, it outputs a probability distribution over all the possibilities. This represents its internal degree of belief. The classic way to think about this is using Bayesian approaches. These methods mathematically combine prior beliefs, what we thought before seeing the data, with the likelihood of the data, the evidence, to produce an updated posterior belief that explicitly includes uncertainty. It's formalized belief updating.
But those big, deep learning models, they aren't always strictly Bayesian, are they? How do they estimate uncertainty?
That's true. For deep learning, we often use clever approximations or tricks. One popular method nowadays is called Monte Carlo dropout, or MC dropout. Remember how dropout randomly switches off neurons during training? With MC dropout, you actually keep dropout turned on even during prediction time when you're using the trained model.
Oh, really? Even when making the final prediction?
Yes. And you run the same input through the model multiple times, say 50 or 100 times. Each time, because of dropout, a slightly different random subnetwork is active. So you get 50 or 100 slightly different predictions for the exact same input.
Ah, I see where this is going.
Exactly. The final prediction is usually the average of all those outputs. But the variance, how much those 50 or 100 predictions spread out or disagree with each other, that variance gives you a direct measure of the model's uncertainty. If they all agree, the model is confident. If they're all over the place, the model is very uncertain.
That's really neat. It turns a training technique into a measure of confidence. And the implication seems clear. Machine decisions aren't facts, they're probabilities. If the confidence is low, maybe it shouldn't act alone.
Precisely. In safety-critical applications, that calculated uncertainty is key. If the model's confidence falls below some threshold, it absolutely should trigger an alert, maybe hand control back to a human, or request more information. It prevents the algorithm from making potentially dangerous decisions when it's effectively saying, I don't really know.
Okay, this is fascinating. To make all this concrete, The architecture, the math, the uncertainty. Let's trace data through a system we all interact with, a streaming video recommendation engine. What kind of inputs are flooding into something like that?
Oh, the inputs are vast and incredibly diverse. They capture basically everything about you, the content, and how you interact.
Yeah.
You got explicit feedback, things like star ratings, adding a show to your watch list. But honestly, the system relies much more heavily on implicit signals.
Like
What did you search for? Which trailers did you watch?
Sure.
Which shows did you start but then abandon after 10 minutes? How quickly did you scroll past the suggested title? Did you pause? Did you rewind? Did you rewatch something? All these subtle actions are logged. And then you match that together with content metadata, genre, cast, director, release here, plot keywords, descriptions, and basic user profile data, like rough demographics, what device you're using, maybe your subscription tier. It's a huge mix.
billions of signals constantly flowing in. How does feature engineering make sense of that chaos? What kind of features get created?
It gets really complex. You typically build features around three main things: the user, the item, the video, and the interaction between them. User features try to capture your long-term habits and tastes. Things like how often you watch, sessions per week, what completion rates you have on different types of content. Often users are represented by these high-dimensional embedding vectors that summarize their taste profile across maybe thousands of subtle content attributes. Video features capture things about the content itself. How popular is it right now? What's its view velocity? You also run NLP on the descriptions, maybe computer vision on the thumbnails to extract visual features. But the real magic, the core of modern recommenders, often lies in interaction features. This is where collaborative filtering comes in strong.
Explain that a bit more. Collaborative filtering.
The system looks for users who are similar to you users, whose viewing history and tastes overlap significantly with yours. It plots everyone in that high-dimensional taste space we mentioned. Then it recommends videos that your neighbor's people similar to you watched and liked, but that you haven't seen yet.
So it's leveraging the wisdom of the crowd, but a very specific crowd that's like me. If I watch obscure documentaries, it finds other people who watch those specific documentaries and sees what else they watch.
Exactly. It goes way beyond simple genre matching. It captures these incredibly nuanced, high-dimensional similarities in taste. People who liked X and Y also tended to like Z. Now, given the sheer scale, maybe millions of videos, hundreds of millions of users, you can't just throw one giant model at the problem. Recommendation systems usually use a specialized two-stage approach.
Okay, a dual system. What are the two parts?
First, you have candidate generation models. Their job is to be super fast and focus on recall. That means they need to quickly sift through the entire massive catalog, maybe millions of videos, and pull out a reasonably small set, say 500 or 1,000, of potentially relevant candidates for you.
So a quick filter.
Right. They use efficient methods, often based on those embedding vectors and finding nearest neighbors, to just get a plausible shortlist. They prioritize speed and making sure they don't miss anything obviously relevant. Then second, you have the ranking models. These are the really sophisticated, heavy-duty models, often deep neural networks, sometimes with hundreds of features fed into them. Their job is to take that short list of maybe 500 candidates and very precisely rank them, predict exactly which ones you're most likely to click on, watch, and enjoy.
And they can afford to be complex because they're only looking at 500 items, not millions.
Exactly. They consider all those fine-grained interaction features we talked about to produce a very precise score for each candidate.
And training these rankers, that sounds complicated too. You're not just optimizing for did they click.
Right. Oh, definitely not. The loss function for a big commercial recommendation system is a very careful balancing act. It's optimizing for multiple, sometimes competing objectives simultaneously. You want to maximize clicks? Sure. But also watch time? Maybe completion rate? Do they finish the series? And then there are business goals mixed in user retention, making sure the recommendations are diverse, not just 10 action movies, maybe promoting the platform's original content. It's a complex blend.
Yeah.
And training this requires enormous computing power, huge clusters of GPUs or TPUs running constantly.
Okay, finally, the moment of truth. Inference. I open the app. That list of recommendations appears almost instantly. How does that happen in real time?
Yeah, it has to be lightning fast. We're talking milliseconds.
Yeah.
When you open the app, the system grabs your latest user features, maybe including what you just watched. The candidate generator instantly pulls that shortlist of a few hundred videos based on your profile. Then the ranking model scores all those candidates performing potentially millions or billions of calculations to get the precise order.
And then it just shows me the list.
Almost. There's usually a final post-processing step. This applies business rules, filters, and constraints that aren't easily learned by the model. Things like filter out content you've already seen, make sure regional licensing is respected, apply parental controls, maybe ensure some diversity in the top spots, potentially boost certain priority content.
So some hard-coded rules on top of the model score.
Exactly.
Right.
And the final ranked filtered list is displayed to you. And crucially, how you interact with that list, what you click, what you ignore, immediately becomes new training data, closing the loop and feeding back into the system to refine future recommendations. It's a constantly learning, adapting engine.
It really is a continuous feedback loop. Okay, this power is immense, but it brings us to the hidden complexity. These systems have deep challenges, fundamental limitations. Let's start with the technical hurdles. What's this thing called the curse of dimensionality?
The curse of dimensionality. It's a fundamental problem when you have lots and lots of features, which we almost always do now. As you add more dimensions to your feature space, going from 2D to 100D to 10,000D, the actual volume of that space increases exponentially.
Okay, so
your data points become incredibly sparse within that vast space. Imagine scattering 100 points in a room that might seem reasonably close. Now scatter those same 100 points across an entire continent. They're suddenly incredibly far apart and isolated. In high dimensions, everything starts to seem far away from everything else. Our usual geometric intuitions about distance and closeness break down. Distance metrics become less meaningful. It gets much harder to find meaningful patterns because the data is spread so thin. It's like searching for needles in an exponentially growing haystack.
right, makes pattern finding much harder. And what about the data itself? We keep hearing models are only as good as their data.
That's absolutely fundamental. The data, quality, and quantity trade-off. There are so many ways data can trip up a model. You have biased data. If your historical hiring data reflects past societal biases, guess what? The model trained on it will learn and likely amplify those biases. You have noisy labels. Maybe the humans labeling the data made mistakes. The model learns from those mistakes. A big one is class imbalance. Imagine training a fraud detection model where 99.9% of transactions are not fraudulent. The model can achieve 99.9% accuracy by just always predicting not fraud. It might completely fail to learn how to detect the rare but critical fraud cases because they're drowned out by the majority.
That's a sneaky failure mode.
It is. And perhaps the most dangerous, especially for systems interacting with the real world, is distribution shift. This happens when the data the model sees during deployment looks significantly different from the data it was trained on. Think of a self-driving car trained mostly in sunny California weather. Put it in a blizzard in Norway, the input data, what the sensors see, has drastically shifted. The patterns it learned might no longer apply, and performance can degrade catastrophically because it's operating outside its learned experience.
It's only learned the patterns within its training bubble. Okay, let's talk about the interpretability crisis. These huge neural networks, people call them black boxes. If a system denies someone a loan or a self-driving car makes a mistake, how can we possibly know why?
That opacity is often the trade-off we make for higher performance, especially with deep learning. The complex, non-linear interactions between millions of parameters can create decision processes that are incredibly difficult, maybe impossible, for humans to intuitively grasp. We're left wondering, did the model learn a genuine, robust pattern? Or did it find some weird, unintended shortcut, a spurious correlation in the training data that doesn't hold up in the real world?
Can you give an example of a spurious correlation?
There's a famous case where researchers found an early image classifier meant to distinguish between pictures of wolves and huskies was actually making its decision based on whether there was snow in the background. Because in the training data, most husky pictures happened to have snow and wolf pictures didn't. The model learned the background, not the animal.
Wow. It found a shortcut that worked on the training data but was totally wrong conceptually. So how do researchers even try to peek inside these black boxes?
There are techniques, though none are perfect. Saliency maps try to highlight which parts of the input, like which pixels in an image or which words in a sentence, were most influential for the final prediction. Attention visualization, especially for transformer models, can show us which parts of the input the model paid attention to when making its decision. There are also methods like concept activation vectors that try to probe the internal layers of the network to see if it has learned specific, human understandable concepts, like stripes or furry texture, and how much those concepts contributed to the output.
But these are still just partial views, right?
Exactly. They give clues, but they don't give a complete causal explanation. And there's a growing realization that for the most complex models, there might be an element of irreducible opacity. The very patterns that give them high accuracy might simply not map onto simple human logic.
And this reliance on data, especially historical data, leads straight into the ethical dimensions. Algorithms inheriting human biases. Can you give some more concrete examples of how this plays out?
Sure. We mentioned facial recognition struggling with darker skin tones, often a direct result of biased datasets lacking diversity. Or consider hiring algorithms. If they're trained on decades of past hiring decisions which might have implicitly favored certain demographic groups, the algorithm might learn to penalize candidates from underrepresented groups, even if protected characteristics like race or gender are explicitly removed from the input features. It learned proxies for those characteristics from other data points. Predictive policing is another controversial area. If models are trained on historical arrest data, which itself can reflect biased policing patterns, the model might end up recommending heavier police presence in minority neighborhoods, creating a feedback loop that reinforces the original bias, regardless of actual underlying crime rate.
So the bias gets baked in and amplified. And trying to fix this bias to make models fair, that's not straightforward either.
Not at all. That's the complexity of algorithmic fairness. When you try to define fairness mathematically, you find there are multiple, often competing definitions. For example, do you want demographic parity, meaning the acceptance rate, say for loans, is the same across all demographic groups? Or do you want equalized odds, meaning the true positive rate and false positive rate are equal across groups? Or maybe predictive parity, meaning the model's predictions are equally accurate for all groups.
And these can conflict.
Often, yes. Optimizing for one definition of fairness can make you worse off according to another definition. Choosing which mathematical fairness metric to prioritize isn't a technical decision the algorithm can make. It's a human value judgment about what kind of fairness we care about most in a given context. Society has to decide.
The algorithm just optimizes what we tell it to. Which brings us to this concept of value alignment and something called Goodhart's law.
Right. Goodhart's law is crucial here. The simple version is, when a measure becomes a target, it ceases to be a good measure.
Okay, unpack that.
AI systems are incredibly powerful optimizers. They will relentlessly pursue whatever target, whatever metric you put in their loss function. The danger is they often find clever, unintended ways, loopholes to maximize that metric that actually violate the original human intent. The classic example is social media engagement. If you tell the algorithm maximize time spent on site, make engagement the target, it might discover that outrage, polarization, misinformation, and addictive mechanics are highly effective ways to boost that metric.
So it hits the target, but the side effects are terrible.
Exactly. The system doesn't understand it's degrading discourse or harming well-being. It just sees the engagement number going up. The measure, engagement, became the target, and it stopped being a good measure of actual user value or societal benefit. The huge challenge of value alignment is, how do we specify complex human values like don't be polarizing, promote well-being, be fair in a nuanced way into a precise mathematical objective function that an algorithm can optimize without finding destructive loopholes? It's incredibly hard.
And related to all this data is the issue of privacy. These systems seem to need vast amounts of data, often personal data. How can we train them without creating a massive surveillance infrastructure?
That's a huge tension. There are technical approaches being developed to try and mitigate this. One is differential privacy. The core idea is to add carefully calibrated mathematical noise either to the data itself or to the results of queries run on the data or to the model updates. The noise is just enough so that you can still see the overall patterns in the aggregate data, but it becomes mathematically very difficult, often provably impossible, to tell whether any single individual's data was included in the dataset or not. It provides a formal privacy guarantee for individuals.
Interesting. Adding noise for privacy. What else?
Another important technique is federated learning. Instead of pulling everyone's sensitive raw data like what you type on your phone keyboard or your health app data into a central server.
Which sounds creepy.
Right. Instead, the central model is sent out to run locally on individual users' devices, like your phone. The model trains on your local data right there on your device. Then, only the resulting model updates the changes to the parameters, which are aggregated and anonymized, are sent back to the central server to improve the global model. Your raw data never leaves your device.
So the learning happens locally, protecting the raw data. Okay, let's move towards the end now. What are the truly fundamental limits of machine decision-making? What can math and pattern matching simply not capture no matter how much data or compute we have?
I think the most profound limit is the gap between causation and correlation. Machine learning, as we typically practice it today, is incredibly good at finding correlations. If X happens, Y tends to happen too. If people buy bread, they often buy butter. Great for prediction. But many really important decisions, especially in science, medicine, policy, require causal understanding. Does this drug cause patients to get better? Will this policy cause the desired economic outcome? Standard ML, based on observing patterns in data, generally cannot establish causality on its own.
So it sees that A and B happen together, but it doesn't know if A causes B, B causes A, or some hidden C causes both.
Exactly. Establishing causality usually requires different methods-controlled experiments, like A/B testing or clinical trials, or sophisticated causal inference techniques that often need strong assumptions beyond just the observational data. Pattern recognition alone isn't enough for causal claims.
And what about that uniquely human skill, the thing that makes models brittle when the situation changes? Common sense reasoning.
Yes, that's a huge one. Humans have this vast, implicit, flexible understanding of how the world works. Physics, social dynamics, intentions, basic knowledge about objects and their properties. We pick this up through living. Machines lack this deep, grounded understanding. They are fundamentally interpolators within the data they've seen. They can perform incredibly well on tasks very similar to their training data, but present them with a situation that's even slightly outside that distribution, something requiring basic common sense they weren't explicitly trained on, and they can fare in bizarre and catastrophic ways.
Like the model not understanding a banana peel on the ceiling is nonsensical because of gravity.
Precisely. While the latest large language models show some glimmers of improved reasoning, true, robust, flexible common sense comparable to a human child remains a massive challenge. And this lack of common sense directly leads to that problem of novel situations and distribution shift. Because they don't have a deep world model, their performance degrades sharply, often unpredictably, when the real-world conditions drift away from the training conditions. They can't reason reliably about things they haven't effectively seen before.
Despite these limits, the field is moving incredibly fast. Looking ahead, what are the major emerging trends shaping the future of this technology?
Well, one absolutely massive trend is foundation models and transfer learning. We're seeing the rise of these enormous models, like GPT-4, large vision models like CLIP, trained on truly web-scale, diverse data sets. These models learn such general-purpose representations of language, images, or other data types that they can then be adapted fine-tuned to perform well on a wide variety of specific downstream tasks with relatively little additional task-specific data. This dramatically lowers the cost and effort to build capable AI systems for new applications.
So build one giant model, then adapt it everywhere.
That's the idea. Another key direction is multimodal learning. Instead of having separate models for text, images, audio, etc., researchers are building single models that can process and relate information from multiple modalities simultaneously. Imagine an AI that can watch a video, listen to the audio track, read the subtitles, and understand how they all relate to form a coherent understanding of the scene. This is much closer to how humans perceive the world.
Makes sense. And for systems that need to interact with the physical world.
That falls under autonomous systems and embodied AI. This is crucial for progress in robotics, self-driving vehicles, complex automation. The challenge here is tightly integrating perception, seeing the world, prediction, what will happen next, planning, deciding what to do, and control, actually executing actions in real time, all while ensuring safety and reliability in unpredictable environments. It often requires learning through interaction, not just static data sets.
And perhaps a more pragmatic trend.
I think definitely the growing focus on human-AI collaboration. There is an increasing recognition that full automation is often too brittle or risky, especially for complex, high-stakes decisions. So the future in many domains looks like decision support systems. Let the AI handle the scale, the speed, complex pattern recognition from vast data, but keep the human expert in the loop to provide oversight, judgment, ethical considerations, domain expertise, and that crucial common sense, especially when encountering novel or ambiguous situations. Augmenting human capabilities, not necessarily replacing them entirely.
So this deep dive has really hammered home that what looks like thinking in these sophisticated systems is actually underpinned by a precise, often hidden mathematical logic.
Yes, and it really reinforces that core conclusion we started with. Machine thinking is statistical optimization applied at massive scale. It's not contemplation, not understanding in the human sense. The power is undeniable finding patterns, optimizing objectives incredibly well within defined tasks. They are profoundly powerful tools, but they are fundamentally incomplete as a model of general intelligence or consciousness.
We've seen how much of our modern world relies on this mathematical logic, often operating invisibly. And that leaves us with a final, maybe unsettling thought for you, our listener, to consider. If we can, and increasingly do, define the precise mathematical logic that drives critical decisions in our society, from the news you see to the job applications that get filtered to the loans that get approved, and we know these systems will optimize exactly what we tell them to. What hidden, crucial human values, something maybe currently just woven implicitly into our culture, intuition, will we eventually discover we forgot to specify in the loss function?